weekend? She seems to be recording. Okay. I did record lecture on Friday, and then I did post it. I forgot to do that, and then somebody reminded me to do that. So feel free. If I say I'm going to post a homework, and I forget to do it, and you want it, text me or email me. Sorry, email me and let me know that happened, right? Because I know sometimes you have those schedules and stuff. I'm not doing it on purpose. I'm just forgetful sometimes, right? So same thing with I'm recording all of these, right? And sometimes I just forget to post it on the YouTube channel. And so, if you want it, email me and let me know. Okay. So we were right in the middle of making our little cookbook of how to solve these things. Again, you shouldn't be a cookbook engineer, but like in dynamics, I think it's okay. This stuff gets pretty complicated, so we're going to try to pair the type of problem with our solution procedure that we're coming up with. It gets pretty complicated, right? I swear by this. I think this first part of the class, when we're dealing with these different acceleration function time, constant acceleration, constant velocity, acceleration function of velocity and acceleration function of position. When we're dealing with these ones, there's all these different methods for doing it. We're going to introduce a chain rule for solving some of these things, and then we have some integrals. I think this part is the hardest part of the class. I really do, right? This when you did physics, I think you did acceleration of function of time or constant acceleration, right? That's it. So these are new. This is kind of, we're already diverging away from physics when we're getting acceleration of function of velocity and acceleration of function of position. But I do, because it's not as clear what the procedure is going to be. There's a little bit more feeling around of how you're supposed to solve these problems. When we go on into the 2D rigid body and 3D rigid body, it is very structured. Like you start each problem like this and you solve them like this, right? Even the kinematic, these are kinematics. This is all geometry. We haven't even talked about forces yet, right? This is all just geometry, right? Acceleration and velocities and positions and moving around in there. We haven't even gotten into forces. Once we get into forces, that's called kinetics. It's a little bit easier. I really do. Just so stick with me, make it through this stuff, and then we'll get more precise and more concise, I should say, methods for solving these things. So what we've done so far is we said, yep, there's going to be, right now we're only dealing with 1D. We're going to go to 2D and 3D. Those just end up being multiple 1D problems is all they end up being. But, and we said there's going to be 4 types of problems when you're dealing with these, with this section. Acceleration of function of time, acceleration that's constant, acceleration of function of velocity and position, right? So we covered what we do when it's acceleration of function of time, pretty simple. We just integrate, right? Kind of introduce this method. So if you want velocity, you do the initial velocity plus the integral of the acceleration integrated between these bounds. The initial and then the final. And then same thing with position, you just integrate again and you go between the initial and final time. This is pretty straightforward, okay? And this is kind of where we left off. Where we left off. And so now we're gonna go into constant acceleration, which actually is very similar to acceleration of function of time. It just happens that it just does not change with time. So you start out the same way. Here. And we said velocity. One step ahead. One step behind. Make sure I'm doing the right stuff here. So we had acceleration of function of time. A of t is equal to dv dt. And then what we do is we put the dt's, all the t's together. So we go a of t dt, and then we leave our dv by itself. Right there. But then now we integrate both sides. This is going from T naught to T. This is going from V naught to V. And just so happens now, this is exactly what we did for acceleration of function. That was exactly the same thing as we did acceleration of function of time. It's just now this is constant. A of T is constant. Right? And so we can actually carry out that integral. If we carry out that integral, boy, I skipped a lot of stuff. I used to do more steps in here, and so my apologies, a little waste of paper. But really, if you do that, right, we just put in a constant for a of t, and you carry out that integral. We can carry out the integral now because just a of t is constant. And this is what you get. Velocity is just a naught times t minus t naught plus v naught. And that might be familiar to you from physics. You might have started with that equation a lot. Okay, you do the same thing. You then do the same thing for going from velocity to position. Now you got velocity. You do the same thing. You go back up to the acceleration function of time. You integrate with a constant, and then what you get is this. Oh. So this is, there's our position as a function of time when you have a constant acceleration. Okay. That, again, should also be very familiar to you, right? When you did projectile motion and you're looking in the y direction, there was like a 1/2 at squared minus v naught times t plus the original position. That's it right there, same thing. Okay. It's just a little bit more because this allows for two different initial times and initial position stuff. So if t naught 0, then that should be very familiar to you from projectile motion stuff. Okay, so we're gonna get a little more complicated here. So that's constant acceleration. Sometimes you may want velocity as a function of position, right? Just sometimes problems will come up like that. Right now we have velocity as a function of time and position as a function of time. But what if you want velocity as a function of position? So if your homework problem asks for something like that, there is a way that you could do that. It involves using the chain rule. So you say the acceleration is equal to dv dt. And then what we do, right, so that's just the definition of velocity, or of acceleration. Acceleration is how does velocity change with respect to time. And then what we're going to do is a little sleight of hand, and we're going to say, we're going to multiply the top and the bottom by ds over ds, right? It's just multiplying it by 1. You could do that. You could take anything, you multiply it by 1. You're always allowed to do that. So we do ds over ds. We flip it around a little bit, and we say this is equal to dv ds ds dt. Right? So I just moved the one ds to the left, and then left one of the dS's in the place and moved the dt over to the right. Right? Same, they're all equivalent. ds dt, what is ds dt? That's velocity, yep. That is velocity, right? So we kind of simplifying this a little bit, or just changing it up a little bit. And so this is dv ds times v. Okay, what we did right there was the chain rule. We used the chain rule. We're going to do this a lot. Actually, in the next page here, we'll use it again. A little trick that we're doing. And so what do we have now? We have dv ds times v is equal to a naught. And what we do is we're going to isolate the v's. So v dv is equal to a naught ds. And so I just kind of put the ds over with the a naught and then isolated the v's. And if we integrate this, v naught to v, s naught to s, you get this. Going to highlight our methods here. Okay. So if something comes up like that, the problem statement says, hey, give me the velocity as a function of position, or if that comes up, that's going to be easier to solve the problem, that you use that equation down the right. That too should be familiar. I think that shows up in high school physics books as well. Constant accelerations. Any questions about that? There's that. So that's it. So we now know what to do if we get acceleration a function of time. We now know what to do if we get acceleration a function, or a constant acceleration. Now let's do acceleration a function of velocity. What was an example of acceleration function of velocity again? When does forces change with velocity? Air resistance, drag. Okay, or viscous flow. Right. The faster you go through it, the more resistance it has. Right? That's how we were able to swim. Right? Move your hands quickly in there, right? And then you get more resistance the faster your hand goes. If you go in there and just move your hands slowly, then you don't get. One thing I've found with age is I've become very buoyant. I don't have to swim anymore. My wife is so amazed at how much I could I can tread water, but it's like really I just float, which is kind of sad, but also impressive. Like I could just go out and I don't have to swim at all. I just go out there. Like I'm never gonna drown, right? I could just go out there. And I just lay there and I just float around. When I was younger, that didn't happen. Yeah, I don't have to wear life jackets. It's a gift. So, you'll see someday. Someday when you're old, you'll do that, and you'll be like, I remember. Remember, my professor told me about that. Turn it into a positive. All right. So drag, viscous flow. You guys are a tough crowd this morning. Now you're just looking at me like I'm weird. See, now you're making me uncomfortable. All right. My son started high school this morning. My wife's probably crying right now. Absolutely, I guarantee she is. We need to get through this class so I can console my wife. It's okay. It's okay. All right, velocity. Acceleration a function of velocity. So we got to do a little trick here. Acceleration a function of velocity. That's equal to dv dt. This one actually is pretty straightforward. We just put our v's together and our dt's separate. So then we just put the dt on the left. Oh, oops, I did that wrong here. dv dt is on the bottom. There we go. All right, so I just put the dt on the left and dv, and I put the a function of velocity on the bottom on the right. That's all we do. All right, and that's equivalent to, just kind of rearrange it here a little bit, 1 over AV, put it in form you're more used to seeing, dv, and then we just integrate this from t naught to t, a naught, v. Oh, not v naught. Oh, yeah. V naught to v. Okay, and what do we do with that now, right? That's where we're at right now. What we do with this is we're gonna do some examples with each of these. It'll kind of solidify it a little bit, but carry out integral and solve for v, which gives you v function t. You might be like, what the hell do you mean by that? Again, we'll do it. Acceleration is going to be a function of velocity, so it's going to have some v's in it. It's going to be like, we're going to see one in a minute, it's like negative 0.003 v squared. So then what you do is you just go on the right-hand side, you go 1 over 0.000 3 v squared dv. So you carry out that integral, 1 over that equation that you have. You carry that out, you go from v naught to v, and you'll have this big thing that has v in it. And on the left-hand side, you're going to have t minus t naught is what's going to be on the left-hand side, and you just rearrange that equation and solve for v. And then that equation that you get is velocity as a function of time. You'll have the t on the v on the left-hand side and all the t's on the right-hand side. Again, we'll do an example a little bit, but that's what you do, right? Where we run into problems is somebody comes in and they try to do acceleration of function of velocity. They try to do it with acceleration of function of time, and you get the wrong answer, and you're breaking all sorts of rules when you do that. But it's just common. You want to just like, I'm going to integrate with respect to time. Don't do that. You got to look at this. You got to look at our cookbook here, and you got to do this little rearranging stuff to make it work. Okay. But then once you get velocity as a function of time, we already know how to do that to go to position, right? Again, all these problems are about going from acceleration to velocity to position, or position to velocity to acceleration. It's all just moving around in that space. Right now, we get velocity function of time. So how do we go to position? Well, we've already done that, right? If you have velocity, how do you get velocity as a function, or how do we get position from velocity as a function of time? We've already done that. That's just simply, that's ds dt. Just put the dt on the other side. V of t dt is equal to ds. We integrate this from t naught to t, and this from s naught to s. And that'll give you s of t. All right, so let's highlight this. Key components here, we got this one. Okay. All right, so that's that one. All right, so if you run into a problem there that says acceleration function velocity, we go up and use that cookbook. Okay, acceleration function of position. Last one. What's an acceleration function of position again? Spring, right? Spring and real gravity. Those are two good examples. Spring, real gravity. Okay. So in this case, we do have to use a chain rule. I was gonna skip something. We need this. Pause. Come back up here. Okay. Sometime back up in this problem here. I skipped this part. Acceleration of function of velocity. If you have a problem like that, and you have one in your homework like this, this is a little shortcut. If you want v of s, velocity is a function of position, here's a shortcut. Okay. Actually, we do that. We use this in an example a little bit. So I wanted to come back to this. So if you have acceleration of function of velocity, that's equal to dv dt. We're going to use the chain rule again. dv ds, ds dt. That's just velocity. And we're going to separate. This just becomes dv ds times v. And then we're just going to put all the v's together. So then you get ds over on the left-hand side. And then we get dv v over a of v dv. You see what I did there? You use the chain rule. That gives you the velocity. Then you put all your v's on one side and all your ds's on the other side. So I just put that av on the right-hand side. I rearranged it a little bit, and I get that. And then if we integrate this, s naught to s, v naught to v. Right? And so this is a little bit of a shortcut. Like I said, I think we're going to use that in an example problem in a little bit. Sometimes it makes our lives a little bit easier if we want velocity as a function of position. So we kind of cut time out of it, and we just go right from velocity, just tie velocity and position together. Okay. All right. Now back down to this. Spring real gravity. So we got acceleration of function of position is equal to dv dt. Right? So I can't, what you're going to want to do is you're going to say, oh, I'm going to put this dt over here and integrate. Well, now I got acceleration of function of position, and I can't integrate it with respect to time because it's not a function of time. It's a function of position, so you can't just do that. So we have to apply the chain rule right here. This just becomes dv ds, ds dt. Again, this is just the velocity. So what we're left with here, a of s is equal to dv ds times velocity. And now I go put my s's together. A of s ds is equal to v dv. dv. And I integrate this from s naught to s, and this one from v naught to v. And if you solve for this and solve for velocity, you get velocity as a function of position. From carrying out those integrals, you get velocity as a function of position. Okay, now that I have velocity as a function of position, I need to then go to position. It's our last one, and we'll do some example problems. We go velocity as a function of position is equal to ds dt. And we put the t's together. dt is equal to 1 over v of s ds. Okay. Isolate the variables, put the s's together and the t's together. And I integrate this from t naught to t. And this one from v naught to v. Or sorry, not s naught to s, sorry. Wrong bounds. Because you're integrating with s's. That guy. This gives you s of t. Okay. Kind of flew through that as quickly as possible just so we can kind of get to the next step. Again, see what I'm saying? It's like, oh my God. Yeah. Which one of these things do I use? I got the chain rule floating around. I got integrals. I got to carry out an integral, solve for different variables, all sorts of stuff going on. Okay. I don't like it. But not too difficult. Okay. So let's dive into this. As a missile is launched at 100 Gs for 3 seconds, then a rocket undergoes negative 4 Gs of acceleration. How long does it take to reach 15 kilometers? Very timely, because there was supposed to be a rocket launch this morning. And what was that? The Artemis rocket? We're going back to the moon. Thank God, right? Like, we were at the moon in the 60s, for God's sake. And we haven't been back. Like, that's kind of bullshit, I think, right? You guys ever ridden, this is what always amazes me. You ever ridden in a car from the 60s? Freaking terrifying, right? Shit's moving all over the place, and things are rattling, and the radio barely works, right? And then they don't even have seatbelts. We went to the moon on that technology. Right? We did, right? You've heard all the stories about like your calculator has more computing power than they went back there, right? And we haven't been back. Like, for God's sake, let's go, right? I mean, what are we gonna do there? I don't know, but let's just show that we could do it again. Cool. But then we didn't do it this morning because there's one of the problems with one of the engines. So hopefully, did you hear anything about like when it's supposed to go? Anybody?
The next launch window is Friday.
Maybe perfect. Maybe perfect timing. Maybe we can watch it. If they do it in class, we'll watch it in class. I was in, what grade was I in? I was in the first grade, and I watched the Challenger shuttle explode during class. That was amazing. Right? You guys, 1984, I believe, I was 7 years old, and they were like just like this. They're like, hey, everybody, let's watch the Challenger. There's the first teacher ever to go on the Challenger. And we watch it go up into space, and then it just blows up. And we're like, shit. Right? And the teacher's running over there, just stopping the TV and stuff. Yeah, anyways. Maybe we can watch history together on Friday. We'll see what time that is. Okay. You guys ever seen what Lance Armstrong, or who's no, not Lance Armstrong. Neil Armstrong, right guy. He was the first guy, right? You ever see where he punched someone? It was a moon denier that came up to him and confronted him at some conference, and he was like in his 80s. He just punched the dude right in his face. It was awesome. What are you gonna do? It was awesome. All right, give it. A missile is launched at 100 Gs for 3 seconds. Then the rocket undergoes negative 4 G deceleration. You don't do this shit in civil engineering. I'm sorry. Like, this is cool. Rockets are being launched. Things are flying through space. That's why I like teaching this class, because I get away from that, right? My whole life is like, okay, we just built you, now don't move. Right? Just stay there forever. Just don't ever move. And then here, the rockets launching into space. And then another one was water breaks. It's just cool stuff. I think Dan Miller, you don't know him, but he used to teach this class before me. He used to say that mechanical engineers design weapons and civil engineers design targets, which I thought like runways. He was in the military for years, and I guess that's their saying that they go around. So. Okay, so this has got a couple different portions to it, right? So we have a missile's launch. There's acceleration, 100 Gs for 3 seconds, and then there's a deceleration component. So we got to break it up into two problems, right? So there's a discrete problem. The first one is acceleration, and then the second part is going to be deceleration. So the first part is acceleration. Okay, accel, and this is going from t equals 0 to 3 seconds, right? And what kind of problem is this? Constant acceleration, 100 Gs for that time. Okay, that's not changing with time, so it's gone 100 Gs. So this is constant accel. Okay, so we get velocity of function of time. You can actually look this up, right? Acceleration. So again, we're going between accelerations and velocities and positions. If you look back, well, let's look back. Acceleration, constant acceleration. There we go. This is how we get our velocity. This is how we get our position. Okay, watch this. I'm gonna cheat. No, I'm not. I won't cheat. I was going to copy it. If you guys have to write it, I'll write it up. Okay. So A naught times T minus T naught plus V naught. Okay, in this particular problem, all right, this thing is starting at 0, so T naught is 0, okay, and V naught. Also, we're going to say that the initial position is 0 as well, right? So it starts out, both of those things are 0. So then this just becomes V of T is equal to 100 G's, so it's 100 times gravity. Okay, and this is a metric problem, kilometers, so this is 9.81 times T. So just to make that clear, this is 100 G's. Oh. All right, 9.81 is the G there. All right, and so at T equals 3 seconds, V of T equals 3, we get 2943 meters per second. So that is how fast it is going after the first 3 seconds. Okay, and we'll need that because during the deceleration component, we need to know how fast it's going. Okay, so that's the velocity at 3 seconds. And then we'll go to position. If you look back up at position, you'll find this equation, S of T is equal to 1/2 A naught T minus T naught squared plus V naught times T minus T naught plus S naught. Right? That just came from up above for constant velocity. And so this guy, S naught, initial position is 0, T naught 0, T naught 0, V naught 0, right? Things starting out with 0 velocity, starting at rest. So we're not left with much there. I write this equation down. This is S of T is equal to 1/2 times 100 times 9.81. That's 100 G's right there, times T squared. And if you do S of T equals 3, we get 4414.5 meters. Okay, that's just the first part of it. So now we know how fast it's going after the initial acceleration, and then we know how far it's gone after the initial acceleration. Okay, and the problem statement says, how long does it take to reach 15 kilometers is what it says, okay? So now we're on to the deceleration. So we know how fast it's going and how far it's gone. Decel, okay? And the deceleration, we got A naught again. So this is a constant acceleration problem again, but now its acceleration is -4 G's. And again, just point out that it is constant. Okay. It doesn't say anything about like how fast it's going. Okay. It doesn't say how fast it's going at 15 kilometers. It just says how long does it take to hit 15 kilometers. Okay. And so we can go right to position here. It doesn't say anything about velocity. So we go right to position, and so we say position is a function of time. Go back up to our equation from above for position, A naught times T minus T naught squared plus V naught times T minus T naught plus S naught. Okay? And this is why it was important to figure out how fast was it going after the initial stage and how far it went after the first stage. Because now at the beginning of this one, that initial velocity is going to be the velocity it was at the end of that other stage, and S naught, the initial position, is going to be the position after the first stage. Okay, so let's plug in all our known values here. S is a function of time is equal to 1/2. Now it's -4 G's times -4 times 9.81 times T minus T naught now is 3 seconds. right? When this problem started, we were already 3 seconds into it, so it's minus 3 seconds here. Plus V naught, we had it solved for before, that's 2943. 2943 times t minus 3 seconds, plus the initial velocity, which is that 4414.5. Okay, so now we have position as a function of time, and to try to figure out how long it takes to hit 15 kilometers. What do I do now? 15. Yep, so 15 kilometers is what is the position at this time, okay? So you gotta be careful of units here, 15 kilometers, so that'd be 15,000 meters. Everything else is in meters here, right? So we'll talk about something here in a second. So we say 15,000, 1,500 kilometers is equal to, I'll just do this, is equal to S of t. Okay, and then we solve for t. And we get t is equal to 6.68 seconds. So this brings up a good topic here. I am super loose with units, okay? You see that. Some people are super tight with units. My teacher in high school used to talk to me about writing your units and all of your equations and all this stuff. I just lost it. I can't do it. Maybe it's my laziness or something. I just can't do it. But I have made it this far in my career. I'm a doctor, for God's sakes, in engineering, and I never use units, okay? But I'm super smart. So I'm not you guys. I'm not actually super smart. But I'm very consistent. I'm very, I do everything in meters. I do everything in seconds. When we get into the worst system in the world, English units, will do some problems in there. I do everything in the right units. I'm just very consistent as I go through. If you need to use units in all of your equations. Absolutely. If you're one of those people, that's great. Good for you. And it makes your life easier, do it. Okay? And then don't do what I do. Okay? But just be careful about it, right? And so if a very common mistake here would have been to just set that equal to 15. You set that equal to 15, you're getting the wrong answer. It's going to be 15,000 because it's in kilometers and everything else. 9.81 is meters per second, and then right. So I put in meters per second. I assumed meters per second in there, and I didn't call it out. So do call it out. And then I also put my units at the end, right? So I got 4414 meters. I got meters per second. I'm clear as I'm going through. I just don't write it out in my equations. The other thing to mention, so that's one thing. If you need to do it the other way, do it the other way. But I'm just not going to do it. I'm not going to put the units in all my equations and stuff. I can see Dr. Madison putting the units in all of her equations. Does she put the units in all of her equations? Yeah, I can see that. That's good. Good for her. Good for her. She's not as lazy as me. Maybe it's laziness is what it comes down to. She doesn't talk about random stuff as much. Now, this last step, to go from here, right, setting this thing equal to 15 kilometers and solving for t. How do you do that? Yeah, but your freaking calculator. Use your calculator, right? I am a huge proponent. This is another way where Dr. Madison and I differ a little bit. I say use your calculator as much as possible. I use my calculator too much. That's a true statement. You got 5 plus 7, I'm adding that shit in my calculator, right? Otherwise, in my mind, would go, okay, well, 5 plus 7. Well, I know 5 plus 5 is 10, and I got 2 left, or it's 12. I swear to God, I would do that. Or, a TI-89, beep, 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 plug that sucker in, right? They used to say, right, like when you were in high school, like you're not always going to have a calculator with you. Bullshit. I have a calculator with me at all times. I got it I always have it. I got Wolfram Alpha on here. I just used Wolfram Alpha this morning just to solve for one of these problems, right? It's always, you will always have it. You will always have it. Except for when you take the FE, they take it away from you. They take away your nice calculator and they give you a crappy calculator. So there is some, but you'll have a calculator, okay? I absolutely am a huge proponent of it because, right, I get down to this step. I turn my brain off. I just like, okay, I plug this thing in, I hit solve, and out pops t equals 6.68 seconds. I'm not doing plus or minus square plus or minus, or a b plus or minus the square root of 4bc, whatever the quadratic equation. You don't have to do that shit, right? I just quickly just and let it just brainlessly out pops an answer. Okay, I'll see it. I'll see it when you guys do your quizzes. There's gonna be who's got a solar power calculator in here. So now you're scared to raise your hands. Sometimes they're still your age. They're still doing solar power. Don't do it. Get one of these calculators, right? And in fact, the calculator you should get is a TI-89. That shit's money. Who's got a TI-89? It's money, isn't it?
Yeah.
You just make fun of those 84, 83 people. Yeah.
I see the new CAS calculator.
Is it pretty sweet?
It's life-changing. It's like a computer.
See, that's the thing. That's one thing. That was the one problem I had with the TI-89 is it's exactly the same as the TI-89 when I went through school, right? So that part I had issues with because I was like, really? Like, what's your phone? How's phone changed since I was at school, right? I used freaking rotary phones back in the day, and then now. But so what is it? The CAS?
Yeah, it's a computer algebra system, so it'll solve like anything.
Whose is it?
TI.
TI's. All right. Yeah. The 89 works pretty well. It's got the pretty print. It's money. It'll do everything you need to do. I swear, if you do anything this year, get a TI-89. I swear to God, you will come back to me. All I ever hear, I tell people to get 89s. Never have I had somebody ever come back to me and go, that was a terrible idea. I've had thousands come back to me and say, TI-89 was the best thing I've ever done in my college career. I swear. Ask for it for Christmas, right? Ask for it for your birthday if you can't afford it. You can get it online. What do you get it for? $100? Yeah. Do it. Yeah, get a used one. Those TI-84s and A3s, garbage, right? It's garbage. They are garbage. I swear they are. I should own stock of TI-89s. Okay. It's money. And I'm going to do that in here. It'll do all these integrals. It'll do all these integrals for you. Prints it out nice and pretty. It's beautiful. It's worth the investment. It's worth the investment. Okay. Let's get through this problem. All right, so this is a mass release from rest. Spring is unstretched. Acceleration, a function of position, right? It just tells us right there. Is 32.2 minus 50 times s, s being the position, and that gives us in feet per second squared. Find how far does the mass fall, and what is the max velocity. Okay, that's the type of problem that it's saying. So it stands out as being acceleration, a function of position, right? This one, they just give us that equation. Acceleration, a function of position. When we do kinetics, the type of problem will be, all right, here's a system like this. Tell me, it just starts out with, here's the system. Tell me what the max velocity and the max displacement is. Right? We have to come up with the equation. That's the part where it's going to differ. This is a good example, right? And so what we're going to do is we'll come in and say, all right, there I've got gravity acting down, and I've got the spring acting up, k times displacement acting up, and then I'm going to apply equilibrium, and I'm going to set that equal to mass times acceleration. And what you'll see is it'll come up with that equation right there. There's gravity. 32.2 is gravity. That's acting down, and then negative 50 times distance. What do you think that is? That's the spring pulling up on it, right? So that's the spring constant k times displacement. So we're gonna derive our next step after we get done kinematics is we then will derive that. That's kinetics, where we actually come up with the equation. Right now, though, we just start with that equation. Okay. So then it says, all right, how far, or what is the max velocity? So this is acceleration of function of position. So you could look up above and see how do you deal with acceleration of function of position. We end up using the chain rule. But before that, let's just talk briefly about what this thing's going to do. Sometimes it's nice to kind of take a step back and say, well, what is this thing going to do when it displaces? So this is position, right? And also what we're going to define. It's okay to do this, and it happens a lot. We're going to define downward s being a positive displacement. Right? We could call upwards positive, and our answer would just be negative and stuff. That's fine. But for this particular problem, we're going to say s is going to be positive down. So what's this thing going to do? It starts out at 0 position, and then it's going to increase in magnitude. It's going to go up like this, and then it's going to go back down like this, out like this, down like this. Right? The thing is going to oscillate. Right? It's going up and down. Right? It's going to go down, and then it's going to come back up, and it's going to go down. It's going to come back up. We're not going to solve all of that, right? I mean, that's getting into solving that as a a problem actually it's vibrations. Those of you that go on to take vibrations class, that's where you're going to figure out what it's doing as a function of time. But in this particular problem, it says what is the max displacement and what is the max velocity. How do you think we're going to do that? When are you going to get the max displacement? Something's going to be 0 at the max displacement. One more time. Velocity. The velocity is going to be 0, right, when we get our max position, but then our max velocity, what's going to be? Acceleration is going to be 0 at max velocity. Acceleration is going to be 0 at max velocity. Okay, so that's just kind of, I just like to lay it out and say, like, well, how are we going to do this? So we're going to try to find where is it that the velocity is equal to 0, and then that'll tell us what our max position is going to be. Okay, so if you look up at our cookbook on how to solve this, we got acceleration a function of position. That's dv dt. Use the chain rule. dv ds ds dt, where that's velocity. And then, so then we get a of s ds is equal to v dv. Just kind of separate the variables there. All right, and we actually know what a of s is. That's what was given to us. So that integral is going to be 32.2 minus 50s ds. That's going from initial position of 0 to s. This is going from the integral of v dv. Okay. Honestly, what I would do at this point is I'd plug that shit in my calculator. It's an easy integral, but I'd still do it. Right? Integrate 32.2 minus 50s with respect to ds from 0. Then you got to put in a dummy. You can't put in s. If you put in s, it'll tell you, no, you can't do that. But you put in like some dummy, like x or something like that, and then it'll outpop this. I could do this one in my head, actually. 32.2 s minus 50s squared over 2. Left-hand side is just going to be v squared over 2. So at that point, I just carried out the integral. Left-hand side, carry out that integral. That's what it is. Right-hand side, carry out that integral. That's what that is. Okay? And now I just solve for v. And then v will give me as a function of position, right? Because there'll be s's on one side of the equation and v on the other side of the equation. And that's velocity as a function of position. So v of s is equal to, right, we solve for v, square root of 2 times 32.2 minus 50s squared over 2. Right. That's v of s right there. Okay. And again, we're going to get the max position when that velocity is equal to 0. So I set that equal to 0 and I solve for position. Max position when v equals 0. Right? So I take my calculator, I say 0 is equal to the square root of 2 times 32.2 minus, am I missing a t? Am I missing a t? I'm missing an s. I'm missing an s. Right there. I'll put it in, I'll make it blue. So you see where it was supposed to go? S right there. 32.2 s. Okay, plug that sucker in my calculator, solve for s where it's equal to 0, and it spits out to me s is equal to 1.288. Answers in feet. To back up on this thing, that height right there is 1.288. I just brought something. What was that? I saw that. 1.288 feet. Okay. That's the first part of the problem. That's the max position, right? Second part of this is what is the max velocity, we'll get to, oh, we got lots of time. We say, well, acceleration function of position. It's going to be when a of s is equal to 0. That's when we're going to get max velocity. When a is equal to 0. And they give us this, right? Acceleration a function of position was given, 32.2 minus 50s. You solve for s, that gives me 0.644 feet. That's not the answer though, right? The question said what's the max velocity? I know where the max velocity happened. It happens at 0.644 feet. So halfway, happens right here, halfway. Right here somewhere. That's where the max velocity is going to be. Okay, well, how do I get the max velocity? Yep, I just take that s and I put it back into my equation for the velocity as a function of s. So I know where it happens, I just put it back up into there, and it tells me what my max velocity is. So you take this, all right, plug it back into this, and so then I get v at s equals 0.644. I get 4.55 feet per second. Money. It's a squiggly line in there. All right. I got 2 cents. That's okay. It's all right. So the next time what we'll do is we'll take off with this example. Rocket car accelerates. So this is going to be acceleration a function of velocity. And so on Wednesday, we'll do this quick problem. And I think that's it. I think that's all you need to do your homework, right? So you can probably start your homework right now. I think it's pretty straightforward. Very small subset of problems, rectilinear problems. So, if you haven't seen that, it's posted on D2L under announcements. So look under there and you'll find it. Wednesday, I have the help center. They've posted hours now, so you can go to their website. And then I'll post it on D2L exactly when their hours are too if you want to go there. I'm not sure if there's going to be a recitation session. Does anybody know if there's a recitation? I should probably know this. But I'll let you know if there's going to be one on Wednesday. I'll post that on D2L as well. So if you want to do the recitation session on Wednesday. That's that. And then we'll finish with that. And then we'll start going into 2D motion and 3D motion. And we'll look at polar and cylindrical coordinates and things like that next. And it's all still just geometry for a while until we get into F equals MA. All right.